In this video, I'm going to explain the relationship between inductive reasoning, conjecture, and deductive reasoning. So suppose that you just started doing some multiplication and you wanted to know what happens if you're going to multiply two even numbers together. Doesn't matter what the even numbers are, but you just keep going because you're bored. There's not much going on in the afternoon, and it's just, what happens if I multiply even times even? What is my result going to be? And if you keep at that for a while, you're going to start to think that even times even, no matter what, is always going to equal some other even number. This is the process of inductive reasoning. It is the analysis of examples and data in the hopes of recognizing patterns so that we can make a generalization or a guess. And that guess or generalization is called the conjecture. So we multiply some even numbers together, we look and see what happens, and then we make the conjecture that even times even will always equal some other even number. Now, from there, to prove that that statement is true, we would have to switch over to what's called deductive reasoning. And deductive reasoning is the process of argument. It depends on facts, postulates, known given information, previously established theorems and results in order to draw a conclusion or prove whether or not something is true. So inductive reasoning is the analysis of data in search of patterns. Conjecture is generalization about that analysis. And then deductive reasoning is the effort you make to prove the veracity or the truth of your conjecture. So the rest of this video is not for the squeamish. I'm going to prove that even times even is always going to equal even. And I'm going to do it in a pretty formal way. So here are three integers. Let n, m, and k be elements of the integers. And you know the integers, that's your negative numbers, -2, -1, 0, 1, 2, and so on. All of the integers. N, m, and k, anytime I use n, m, or k in this description, in this example of deductive reasoning, I'm talking about pulling any one of these numbers for those values. No decimals or fractions allowed. And the basic proposition is this: 2n times 2m, can I show that even times even is always going to equal some other even number? Well, first of all, convince yourself that 2n is, no matter which one of these numbers I plug in for n, I'm going to get an even number. I plug in 0, 0 is even, 2 times 0. I plug in 10, which would be way over here somewhere, where 2 times 10 is 20. So this is what's called the form of an even number. 2n or 2m, this is the form of an even number. And if I multiply the form of even times the form of even, can I show that that's always going to give me the form of even? Well, 2 times 2 is 4, n times m is nm. So I've got this thing 4nm, but I'm going to creatively factor that a little bit. 2 times 2nm. I really haven't done much here but change the shape. Change the way I'm expressing what I know. And the challenge here is to see that the stuff in parentheses here that I've highlighted in green, no matter what value I plug in for n and m, I'm always going to get another integer back. It might be even, it might be odd, but it's definitely going to be an integer. So let's just choose, let's do maybe 2 and 3. So let n equal 2, let m equal 3, and now this thing right here is just 2 times 2 times 3, which would be 12. And it doesn't matter what you choose, anything you plug in for n and m is going to get you some number from this set of integers. So because that's true, I'm gonna make a little substitution here. I'm gonna say let k equal 2nm because k is an integer and 2 times m is an integer. So I could just do the little substitution here and say this is really equal to 2k. And now I'm right back to my form of an even number. If by definition this is even and this is even, then this has the exact same form as this right here. So the product of these two things is going to be even as well. I probably won't ask you to do a proof like this in class, but it is an example of deductive reasoning.